get started at the beginning of Chapter 7, what we can learn from data. So the important thing here is to recognize that statistical inference is all about learning from data. So how do we learn from sample data? Well, when we obtain information from a sample selected from a population, we usually do that for one of two reasons, either an estimation problem or a hypothesis test problem. And one of your goals as a student of statistics is to learn when you're trying to do an estimation problem versus when you're trying to do a hypothesis testing problem, because that's going to affect the types of methods that you're going to use to analyze your data. So an estimation problem is when you want to learn something about characteristics of the population. So we'll take sample data and we'll estimate some characteristic like the mean or the proportion. Or we might want to do this hypothesis problem where we're going to use sample data to decide whether there is support for a claim or a statement about the population. So there's a subtle difference here. An estimation problem is simply trying to estimate some characteristic, whereas a hypothesis problem is we have some guess as to what we think that characteristic might be, and we're going to see if our data supports that guess. So at its bottom line, an estimation problem is using sample data to estimate a value of a population characteristic, and a hypothesis testing problem is using sample data to test a claim about a population. Now, we're not always going to be using one population. Often we'll be looking at two or more populations. So when we are looking at two or more populations, our goal is to learn about the differences between these populations. So for example, in 2014, the National Sleep Foundation conducted a survey of 1,103 adult Americans who had a child between the age of 6 and 17 living with them. So we know that electronic devices are thought to disturb sleep, and so these researchers wanted to know how many electronic devices parents and children had in their bedrooms so that they could see if there was a relationship there. So they collected data from the survey, and they found that the estimate for the proportion of parents who have two or more electronic devices was 54%, and the proportion of children with two or more electronic devices was 45%. So what kind of problem is this that these researchers were asking? And so here, since they simply tried to estimate the proportion, this is an estimation problem. If we look at example 4, and we want to know if school start time makes a difference, there's been many studies that suggest that adolescents would do better with a later start time for school. So this paper, Adolescent Sleep, School Start Times, and Teen Motor Vehicle Crashes, looked at a large sample of students from grades 6 to 12 during the year prior to a change in start time, and then a second sample in grades 6 to 12 during the year after the change. So the students in both samples attended a school district that implemented a 1-hour delay in the school start time for the second year of the study. So one of the things that the researchers wanted to ask and understand was the number of hours spent sleeping in a typical day. So they concluded that the mean was 0.5 hours greater after the change to a delayed start than it was before the change. So here we're generalizing from a sample, but it's a hypothesis testing problem because we're testing some claim. Okay, we want to think that the mean number of hours of sleep on a typical night is going to increase when you have a delayed start. So this is also a claim about the difference between two groups. You're comparing the group before the start time change and after the start time change. But ultimately, we've made some claim that we think it's going to make a difference, and we see if our data supports a significant change. So we're often going to be looking at experimental data, though sometimes we will be looking at data from observational studies. So when you have an experimental data, then you need to consider the same types of problems here. You're either going to have an estimation problem or you're going to have a hypothesis test problem. The only difference here is that you're actually going to be imposing an experiment versus those observational study questions where you're just collecting data from a sample and making observations from it. So with your estimation problem, you're going to have sample data that you'll use to estimate a characteristic. So something like the mean response or the difference in mean response of two treatments. So it's still that same idea that an estimation problem is collecting data and calculating an estimate for some population characteristic. It's just this time it's going to come from an experiment. Then a hypothesis testing problem is going to test a claim about some treatment effect. And this is very similar to what you would do in a science class, where you make a hypothesis about what you think would happen if you do different treatments and you observe the outcomes after the experiment. So we can look at this example 7.5, where there was a study that points to benefits of knee replacement surgery over therapy alone. And this study, researchers randomly assigned adults with moderate to severe osteoarthritis to either a group who received a knee replacement followed by physical therapy, or a group who did not have knee replacement surgery, but they received extensive non-surgical therapy. So this becomes an experiment because the researchers are intentionally assigning these participants to a treatment group. After a year, the people participating in the study were asked if they had less pain than before the surgery or treatment. And so they found that the estimate for the proportion was higher by 0.17 or 17 percentage points for those who had the knee replacement surgery. So this would be an estimation problem because they didn't make a claim, they just simply calculated the estimate for the percentage change between the two groups. So we do need to recognize that when we are doing statistical inference, there is going to be a risk. So we've looked at several examples so far in this chapter, and we're going to be collecting sample data and experimental data in a variety of settings. But you have to recognize that learning from data involves risks. There will be times that the results from a study or an experiment are flawed, and we need to be prepared for that. So what can happen in an estimation problem is that the estimates might be inaccurate. It is possible that the sample that you collected really doesn't represent the entire population. And so when that's the case, your estimate, no matter how correct you feel like you are in the method, which you will be, you'll do the calculation correctly, but your sample just really wasn't a great sample. And so you will have an inaccurate result. The same thing can happen in a hypothesis test. It is possible that the data that you collect in your experiment leads to a conclusion that's not necessarily the same conclusion that you would have if you looked at the entire population. So you might have data that concludes that there is support for a claim, but that claim really isn't actually true. Every once in a while, experiments are going to show a result that really was unlikely to have happened, and we just have to be prepared that there's a chance that we reach these incorrect conclusions. So where are these risks coming from? And one of the major sources is just the simple fact that there's a lot of variability in data. When you collect a sample, the sample provides only a partial picture of the population. Sometimes the sample is great and reflects the population well, and sometimes that sample really isn't great, despite our efforts to try to take a good representative sample. So we need to recognize that there is variability in the population, and so that partial picture, we need to ensure that it is representative of the population, and sometimes it might be hard for us to even know that before we do our study. So be aware that even if you select your sample using a proper technique, there's so much variability in a population that these samples are possibly going to be quite different from sample to sample. And we call this sample to sample variability. And you just need to be aware of this so that when you assess the risk of drawing conclusions about the population from sample data, that there's a chance that because of the variability of samples, you might have reached an inappropriate conclusion. Now, also in experimentation, there's an awful lot of variability because when we try to generalize from experimental data, occasionally there's a response that happens that was not from the treatment. And we do everything that we can to ensure that we have a control group, that we use placebos, that we've set up a good comparative study. But it is possible that just because of the sample that you had in your study, there's so much variability that your particular group came to a different conclusion. And so we need to be aware whenever we read a study that has a small number of subjects in the study, that we just have to be aware that that makes it even more likely that variability is going to have a negative effect on our outcome. I was reading a study recently about vaccines for COVID-19, and there were only 45 subjects in the initial study. And to me, 45 seems like an awful small number, but I'm sure the researchers who study these kinds of things for a living are comfortable with that sample size. But it frightens me just a little bit that 45 was a large enough sample to try to conclude that a particular vaccine was going to be safe and effective. So there's 4 key questions that I encourage you to use when you're trying to decide what kind of problem that you're looking at. So are you looking at an estimation problem or a hypothesis problem? You need to know that because the methods are going to be different depending on which type of problem you have. And in the next few chapters, we'll learn the different methods that we'll be looking at in order to perform these 2 types of problems. We also need to consider the study type. Are we generalizing from a sample to learn about the population, or are we generalizing from an experiment to learn about treatment effects? Because the answer to this question will have an effect on the choice of the method that we use to draw our conclusions. We also want to be aware of the type of data. Are we looking at a univariate data set? Are we looking at a bivariate data set? Do we have categorical data? Do we have numerical data? Because the type of data that we have affects what type of methods that we can use for our study. And then finally, we want to know how many samples or treatments there are. So knowing how many samples there are, or if the data are from an experiment, how many treatments are being compared, is going to help us again know what kind of method to use, because there are some methods that are appropriate for a single treatment or a single sample, and then there's other methods that you would use if you had multiple samples or multiple treatments. This is a table that you'll find in your textbook, and it's going to help you decide all of the different methods that we'll have in this class. So it helps you see the type of question you have, the type of data that you have. Was it from a sample or an experiment? Do you have categorical or numerical variables? How many samples or treatments? And then it gives you the method that you should consider, and then each chapter that you would refer to in the textbook to answer that question. Now in this class, we will not get to chapter 16. That's something that you would do in a Statistics 2 class, but we will cover everything else in this course. Finally, I want to end with a 5-step process for both estimation problems and hypothesis problems, because this is going to help you organize your thinking to determine the appropriate method to choose to analyze your data. So it starts with E, where you estimate, and you recognize that you're trying to do an estimation problem. Then you select the appropriate method using that chart in your textbook. You check to make sure that the method is appropriate. So as we learn the different methods, we'll have different conditions that we need to ensure are met before we can conclude anything using that method. Then we'll do the calculations, usually using statistical software. And then finally, we want to communicate our results, because it doesn't matter if we come up with some sort of conclusion if we can't communicate it to somebody else. Once you've decided that it's a hypothesis test problem, you want to start by defining the hypotheses that you're going to be testing. Then select the appropriate method using the table in the textbook. Then we'll be learning about the different criteria and conditions that we need to meet in order to use that method. We'll do the calculations using StatCrunch in this course, or other software if you're in a different course or in a different environment. And then finally, we communicate those results. So this is where we're heading. This is the structure of the statistical inference. And over the next few weeks, we'll be learning exactly how to do all of these methods and what type of conclusions are appropriate given the data that we have.